How to optimize large datasets with Dask efficiently. In this video, you'll learn strategies to optimize memory usage and enhance performance with Dask, empowering you to manage large datasets effectively. Welcome to our exploration of Dask, an innovative parallel computing framework designed to tackle large datasets efficiently. Imagine working with datasets so large that traditional tools simply can't keep up. This is where Dask shines. By distributing computations across multiple cores or even servers, Dask allows for scalable and efficient data processing. Unlike other frameworks, Dask integrates seamlessly with Python's existing data science stack, providing familiar interfaces for pandas, NumPy, and more. In this video, we'll dive into how Dask not only enhances performance but also significantly cuts down on computational costs, making it a vital tool for data professionals.
To truly harness Dask's power, it's crucial to understand its core data structures, arrays, data frames, and banks. Dask arrays are akin to NumPy arrays, ideal for handling large numerical data across multiple dimensions. On the other hand, Dask data frames extend the functionality of Pandas data frames, enabling you to work with large tabular data without exhausting memory resources. Finally, Dask bags are perfect for processing unstructured or semi-structured data, such as JSON or text files. By leveraging these data structures, you can choose the right tool for your specific data processing needs, making your workflows more efficient and scalable. Memory management is a critical aspect of working with large datasets. Dask offers several strategies to optimize memory usage and prevent bottlenecks. One effective approach is to utilize lazy evaluation, where computations are only executed when results are needed, thus conserving memory. Additionally, choosing memory-efficient data types can significantly reduce memory footprint. Dask's Memory Profiler is an invaluable tool that helps you monitor and analyze memory consumption during computations. By combining these techniques, you can ensure that your Dask workflows are both memory efficient and performant, allowing you to tackle even the most demanding data processing tasks.
Lazy evaluation is a cornerstone of Dask's approach to efficient data processing. By deferring computations until results are explicitly required, Dask can optimize execution plans, minimize resource usage, and ultimately improve performance. This approach is particularly beneficial when working with large datasets, as it allows for more efficient scheduling and execution of tasks. By implementing lazy evaluation in your Dask workflows, you can achieve significant performance gains. In this section, we'll explore real-world examples of lazy evaluation in action, demonstrating how this technique can streamline your data processing tasks and enhance overall efficiency.
Chunking is a powerful strategy used in Dask to manage large datasets effectively. By breaking data into smaller, manageable chunks, Dask can optimize memory usage and improve processing speed. This approach allows for parallel processing of data, significantly enhancing performance. When implementing chunking, it's important to consider the size of each chunk, as this can impact both memory consumption and computational efficiency. By optimizing chunk sizes, you can achieve a balance between memory usage and processing speed, ensuring that your Dask workflows are both efficient and scalable. In this section, we'll explore various chunking strategies and their impact on performance.
Profiling and debugging are essential components of optimizing Dask computations. By leveraging Dask's powerful profiling tools, you can gain insights into task execution times, memory usage, and potential bottlenecks. These insights are invaluable for identifying areas where optimizations can be made. Additionally, understanding how to effectively debug Dask tasks is crucial for resolving issues and ensuring smooth workflow execution. In this section, we'll explore various profiling and debugging techniques, providing you with the tools and knowledge needed to optimize your Dask workflows and overcome common challenges.
Scaling Dask clusters is a key strategy for leveraging distributed computing to handle large datasets. By distributing computations across multiple nodes, Dask can significantly enhance processing power and efficiency. Understanding how to effectively scale Dask clusters is crucial for optimizing performance and ensuring efficient resource utilization. In this section, we'll explore the process of scaling Dask clusters, discussing strategies for efficient cluster management and the impact of scaling on performance. By mastering these techniques, you can harness the full potential of distributed computing in your Dask workflows.
Real-world examples provide valuable insights into the effectiveness of Dask optimization strategies. By examining case studies of successful Dask implementations, you can gain a deeper understanding of how these techniques can be applied to achieve significant performance improvements. In this section, we'll explore various real-world examples of Dask optimization, highlighting best practices and lessons learned. These examples will demonstrate the tangible impact of Dask optimization on performance and provide you with actionable insights to apply in your own workflows.
In conclusion, Mastering Dask for large dataset optimization can significantly enhance your data processing capabilities. By implementing the strategies discussed in this video, including chunking, lazy evaluation, and scaling clusters, you can achieve remarkable performance improvements and cost savings. We encourage you to apply these techniques in your own workflows and share your experiences and questions in the comments below. As you continue to explore Dask's capabilities, you'll uncover even more ways to optimize your data processing tasks. Thank you for joining us on this journey, and we look forward to seeing how you leverage Dask to tackle your data challenges.